So we're going to do logarithmic models. So this is just the idea of kind of getting used to the fact that we're using logs to try to start observing certain things. So as always, you can watch the information by yourself. So nuclear power plant. So when we're talking about nuclear power plants, they decay at an exponential rate. So at the beginning, they're gonna decrease a lot, and then they're gonna decrease less, and then they're gonna decrease even less and less and less and less and less. So they're always technically gonna be nuclear, but there's a certain point where they become so small in being nuclear that they're not as harmful. So since we know it's going to decrease at an exponential rate, our goal would be like trying to figure out, if we do the inverse of it, trying to figure out when it's going to get as close as possible to that. Or, forgot, it's a log. But when it's going to get over here. Like it's always going to be here, but we're trying to figure out when it's going to start getting safe. Like if the safe level is over here, how many days will it take to get there, basically? So let's kind of see what's going on here. So if we look at this one, this Uni Activity is talking about the STEM. Read the instructions on the self-checked activity, type in the response here. So here it's saying when uranium decays, so here's the decay of uranium, lead. So uranium decays, it leaves behind some lead. So as this is decaying, there's more lead coming in. So if you think about it, then lead is the inverse. And since uh, uranium it decays at an exponential growth, then this would be a logarithmic growth. So if we're thinking about that and we want to label this, we're going to label. So in addition, there are three vertices, three vertical lines. So hold up. The following graph illustrates how much is left over after t years. In addition, there are three vertical lines labeled 1, 2, and 3. So this is basically just telling us, ooh, these are in billions of years. So if we look right here, this line kind of tells us when they're even, right? Line 1 tells us when they're even. Line 2, I guess we're going to figure out what that is because it's going to tell us a certain gap in between it, I assume. And over here, it's going to tell us a different gap. So I have a feeling they're going to explain that in a bit. But I know line 1 kind of represents when they're even. So here we're talking about 1/2. Oh, that's what the lines are. The lines represent the half-lives. Okay. So after 1/2 life, uranium and lead are even. So how much is left? So if we look at the percentage, I'm assuming this is out of 1. So this is 100% going down to 0%. So after this one, they're 50%. So they're both 50-50. After 2 half-lives, it looks like it's about, let me see here. Let me try to draw like a straight line. That is the worst straight line possible. So it's a little above 0.2%. So I'll probably say like, I don't know, 0.25 or 25%. And this one, I'm assuming it's also going to be about 75%. So it looks like they're always equaling each other. That makes sense because if they're inverses, they should always add up to 1. This one, it looks like it's at 0.1, so 10%. And it looks like it's almost at 0.9. Is this not at 0.1? Draw my attempt at a straight line. Oh, it looks like it's at 0.15-ish, which means this one, if I drew a straight line, it wouldn't be at 0.9. It would kind of be in the middle. Those lines are terrible. All right, so this one, I'm assuming we're going to get about 15 and about 85. So that's what we're doing. So it should always add up to 1. Maybe my guess is a little off. Let's see an example. So they got really specific with it. Again, it doesn't have to be this specific. We're guessing, we're just looking at the graph. They didn't give us really enough numbers and they didn't give us a link to kind of research it. So as long as you guys like, I'll accept these. And if you can see here, like it decreased 50% right away, and then 50% of that. Well, I guess if you're doing it math wise, 50% of 100 is 50, 50% of 50 is 25, 50% of that, it really should be 12.5. And since we're adding up to 100, oh, Garrett, nice to meet you. Glad you could join us today. Almost late? It, it's 11:16. Class starts at 11. I, I give you 5 minutes. You're anyways. So, so if we're at 100, we take half of it because it's one half life. We get to 50 and that. So I was for eyeballing it, I was pretty spot on. But if we're using the actual math, that's how they're getting these numbers. They took half of 100, they got 50. Half of 50 is 25. Half of that is that. And because they have to add up to 100, because all the uranium's being replaced with lead, that's how they're getting their numbers. So then here, initially at time 0, what is the percentage of uranium and lead? Well, we don't have any lead, so we're going to start at 0. At the beginning, we only have uranium. So what we're going to do here is we're going to say when we start off, we have 100% uranium and 0% lead. And if you want to get specific, you can write this. These are known as the atomic weight, so it's how many protons it has. Actually, is it protons? No, it's how many electrons it has. I'm sorry. So it's how many electrons it has. So that's why it's radioactive. It has more electrons than the amount of protons on there. So what is the half life of uranium? So according to this, a half life is a little more than 4 billion years. So that's why uranium. It's a big deal with uranium because it's gonna take a billion years just to get down to half. So yeah, that's bad. About four something years. So I'm gonna say a little more than 4 billion years. A little more. We're talking about big numbers here. More than a more than 4 billion years. Billion years. See what they put down. A little. They actually said a little more than 4 billion years. Okay, so it's okay to put still a little more than a billion years. They're getting really specific. I assume they Googled this, so you don't have to be that spot on. Uh, what percentage of uranium is left after this? So after 4 half lives. So after 3 half lives, we were at 12.5. So after 4 half lives, we are at. So I'm going to use my calculator from Google. Calculator provided by Google. Yeah. Don't forget to like and subscribe so I can get monetized. Need to get my watch time up, guys. So we're gonna have about 6.25% of uranium. And then since I'm lazy, I'm just gonna copy all of this. I'm gonna say we're gonna do the inverse of this. So we're gonna subtract this from 100. So luckily, what I can do here is, does it not let me? No. Oh wait, yes it does. No, it doesn't. This thing is messing with my feelings right now. So 100. Time to beat it up. What? I wonder what people think when I'm like saying all these comments to you guys. Like what they'll think in the future when they're watching these videos. They're like, "Who was he talking to?" 23.5. Lead. So basically, what we're doing is we're just kind of subtracting it from 100. And then I'm lazy, so I'm going to copy both of these lines actually. Boom. And then I'm just going to go back and change this to 5 half-lives. So I change that to 5, change this to 5. I'm going to cut this in half. So 6.24 divided by 2, 6.25. So that's 3.125%. Where is it? Ah, there it is. 3.125. I should be putting percent here. I keep forgetting to put the percent sign. And again, percent is shift 5. So if I subtract this, it's 90 something percent. 100 minus 3.125. So 96. Can I just copy this? I can copy it, guys. I did. Oh, dang. So that's what we're looking at. So it's a half-life. So we're always going to cut this percentage in half. This is always going to be the inverse because it's the inverse function of it. So it says use the internet to research. So when I read this, I read Google it. I'm going to Google it. This diagram maps the nucleus map of this. This doesn't explain why. Google, you're supposed to tell me why. This doesn't tell me why at all. Oh wait, a certain number of natural nucleus. I guess I should have read. Learn to read, guys. It's helpful. I'm still learning. So what it sounds like, from what I skimmed over this in the last like 2 seconds, it sounds like they have the same number of like protons. So when it goes away, it's gonna start slowly turning into lead. But just kind of read through it and use your own words. I don't want to see any copying and pasting for this. I've been doing it for numbers because there's no creativity, but give your own reason as to why all these radioactive things turn into lead. So here, now what we're going to say here is we're going to use our little like half-life formula. So remember when we were using exponential growth, the rate of change was 1/2, and then t is the amount of time, and then n is the number of years that passed by. Or I'm sorry, t is the number of years that passed by, and n is the half-life. So in other words, where all this exponent is right here is the number of half-lives. So if you have something unprecise like this and this, there's going to be like a fraction of half-lives in there. So that's what they say. Since the exponential growth is 1/2, it's telling us how many times it gets cut into 1/2. So assuming that the half-life remaining is that, what percentage is left after this? So if we're looking at percentage, we're going to assume that this, you can assume it's 1 if you want to deal with decimals, or if you want to deal with percentage, call it 100, because that way it's 100%. So what I'm going to do here is I'm going to deal with decimals. I'm okay with dealing it with decimals. So we're solving for AT, the amount after a certain amount of time. I'm going to say we're going to start off with 1. So I'm going to do 1/2 of T is, since they're both billion years, you don't have to type in the 9 zeros, because those 9 zeros are going to cancel each other out. So I'm just going to label it like this. So what I'm going to do here is I'm going to go to my Google calculator. And I'm using the Google calculator because I know all of you guys have access to it. I don't want to like use this calculator or this big old calculator because you guys might not have access to it. So I'm just going to keep using the Google calculator. If you guys want help using your own calculator, let me know, and I can always kind of cover it. So what I'm going to do is I'm going to enter my 1/2 here. I can do it as 0.5, but I'm just doing it as 1/2 right now. I'm going to use my little exponent button. I'm going to use parentheses to kind of be able to just plug the whole thing into Google instead of like solving this fraction right here by itself. I'm just going to plug the whole thing in just so I can get a straight up answer. And then at the 0.25. So if I enter it, I'm going to get this. So make sure to show your work. So it looks like there's going to be about 31% left. So when you're showing, oops, not attendance. So when you're showing your work, you're going to be like, go into your equation editor, go A subscript T equals 1 times big fraction 1/2. Put this in parentheses. I always hate, it bugs me so much how Momentum doesn't make the parentheses bigger. Like, it bugs me so much. It is the small things. I hate them. 4.2 billion over 2.5 billion. And then, because I'm lazy, I'm just going to copy this so I don't have to redo that subscript. Boom. And then I got this. And the beauty of Google is this lets us copy it. So we can highlight this, Control C, Control V, about 31%. Boom. That's all in there. I would say nice fraction, but I don't like those parentheses, but you kind of get the idea here. Then just do your self-evaluation there. All right. Did everyone understand how I did that? The the work. Sometimes I wonder how the other 3 students put up with you two. So the next thing we're going to talk about is logarithmic growth models. So the one way we did it was this idea here with the half-life model, for example. It's this idea of, they say AX, normally the models be AB to the X power. And this idea of this is the initial, your A is always your initial value, your B is your growth rate, and this is always going to be some type of time. So one of them was like the half-life divided, or the amount of time divided by the half-life. But there's other ways to do it. So we're going to learn about how to do it with exponential growth using E. And this is why the, what's it called? The Uni Activity is going to be a paper on E and how we use E in the real world. So E is just like a number that they realize, like, hey, did you know that we can put our rate here and the amount of time here, and that's going to give us our answer. So this E kind of lets you do it a lot simpler. You can just put in your rate and your time, and it just works. So it's this magic number that you guys are going to read about for your unit activity. So here we're talking about learning curves. Didn't we already do learning curves? I feel like we did this already. That like S model, I guess we're going into it a lot more. How at first you learn a lot, and then over time you start learning less and less and less until you kind of reach this like point where you can't get any higher. So I feel like, yeah, this is like the logistics curve. That's that idea. So in this case, they're doing this method of they're learning how to do the high jump. So at first, you're probably going to be really bad at the high jump. You're not going to be able to go that far. But then after a while, you start practicing. You're like, oh, I'm getting really, really good at this. And then after a certain point, you're like, I'm not getting that much better. But that makes sense because at some point, you kind of reach your max potential. So that's why they use this like S model. At first, you're learning exponentially, and then you're learning logarithmically. So I think that's why they brought this back, because now we know about the second part of it. So logs and natural log. So again, natural log is just log base E. That's all ln is. Whenever you think ln, just imagine you're doing E. So ln and E are inverses of each other. So if you want to cancel ln, you have to base it by E. If you want to cancel an E, you have to use natural log to get rid of it. Does that make sense? And then here they're using their exponent rules here. So they're just saying that if you want to get rid of log base E, you just base it by B, and that gets rid of it. If you want to get rid of the multiple, so they're just going over this. So this is like the inverse rule, and this is the product rule. This is the quotient rule. We went over these rules, right? Like, I'm not having deja vu or anything. Okay. Could have sworn we went over these, but I guess they're just reviewing them. It's also known fact that so this right here, they're just talking about the if you have exponent at 0, it's always going to be 1. Assuming that your A is 1, it'll be 1. But if your A, remember how I said A is your initial rate? If your A is like 2, then anything to the 0 power will be 1, so it becomes 2 times 1. So this is just saying simply that if you plug in 0 for x, you're going to get whatever your A is, whatever your initial rate is. Will that make sense? Cool. So that's one of the properties here. We're looking at the initial rate. So this tells me that my initial rate of, or my exponential rate of change is 1/2. So when I first get started, it's always 1/2. So if I go up to so this tells me it's going to be a decrease because I'm decreasing. I'm slowly going down and down and down and down and down, right? So that tells me that if I'm at 1, after 1x, I'm going to be at a half. So this one has to be my answer. My A has to be this one. This is the only one that's an exponential decay, and it's going down at 1/2. This isn't an exponential decay. This is an upside down log. This is exponential growth, and this is a regular log. So this is the only one that made sense. This one's a log. Nothing special is going on here. So we're just going to make this our log option. This one is an exponential growth. So it would have to be this one. So we're just matching the graphs. I thought they were going to be really specific on it. Technically, E, well, you guys will find out what E is. E is like right here at this 2 point something something. You'll figure out once you do your paper on the Uni Activity. This one's a log, but it's log with a base of a fraction. So that's going to be this idea. Because remember, if your rate of change, if your exponential growth factor is a fraction, that means that you're doing exponential decrease. So that means that when you do the inverse of an exponential decrease, you get this upside down log right here. Does that make sense? So this one, exponential growth, E. Exponential decay, so that's this one right here. I didn't realize that I should have started off with the definitions here. This one, logarithmic growth, you're growing. Logarithmic decay, so it's just slowly going down and down and down and down. So that's going to be this H. All right. Are we going to be able to finish this one in one class? What? Let's see. We'll see what happens. So now we're going to talk about like the rhythmic scale. So when we're comparing earthquakes, the Richter scale is by base 10. So see here how there's no base? That's because we're doing log base 10. So remember, whenever you see a log with no base, that just means it's log base 10. So what we're going to do here is if we're comparing two things, we're going to be doing the thing that we talk about versus the initial Richter scale factor. So I, in this case, would be 1. So we're always going to be doing it by 1. So how many times greater? So technically, we don't even need this I, but we're going to keep using it anyways because it's part of the formula. All right. So here it's saying how many times greater is it than an initial quake of 1? So we're going to plug this number into here, and we're going to end up getting this 6.4. So if we want to work this out, again, we don't really need to divide here. So all we can do is grab our calculator. Where's my calculator? There it is. We're going to use the log function. We're going to do 2.3 times 10 to the power of 6. So it's 1,000,000. But we're going to do that 10 to the power of 6. So in other words, 2,300,000. Does everyone know how I got that 2,300,000? So it's going to be times 10 to the 6th power. So that means I have to move this decimal 1, 2, 3, 4, 5, 6. So that's how I get 2,300,000. So I could. So if I do that, I should get this 6.36. On the book, they did the book, and Mentum said 6.4. Just to prove to you that I wasn't making that up, log of 3, 1, 2, 1, 2, 3. The same answer. It's just an easier way of writing down. That way we don't have to write down all those zeros. So this is all we're doing here. We're just comparing these. So the I naught is what we're comparing it to. How many times greater is it? So now we're going to do 3 earthquakes. Each of these earthquakes record their location and calculate their intensity. Okay. So we're going to look at the 3 recent earthquakes that have happened so far. So we're going to do this one. Oh my gosh. What did I do? I don't like this. I'm going to do this one. So we're going to do this one in Mexico. So here's 3 earthquakes. Well, this one's not impressive because it's the same thing. So I'm going to do this one in, looks like the tip of Alaska. Oh my gosh, all the earthquakes have the same. Okay, so we're going to do this one, 4.0, and this one, 4.2. Is this still Mexico or is that Guatemala? No, that's still Mexico. And then we have Alaska. Okay. So, where's the activity? So we're going to do one in Alaska, 4.5, one in Mexico, which is 4.2. Just so we have a variety, which other country do you guys want me to get an earthquake reading from? From these little dots. Texas is not a country, Nick. Okay, I'm going to assume you said China. Africa? There's no earthquakes in Texas. China? Okay, so we're going to do China, 4.4. Jeez. China, 4.4. So these are all going to be different, unless you guys are just following along with me. It's like, okay, go to the world map animation past 7 days. Are you serious? So we're going to go to the world map and do, how do you do the past 7 days? There's no earthquakes in Texas. Stop it. You know how confused everyone who's watching this video in the future is? I know. That's why they're confused. What are they trying to do here? I don't understand what they're trying to do. How do I look at the last 7 days? Let's see what they want us. Go to the world map and start animation. So I'm going to erase this and start the animation. How do I start the animation? Does anybody see how to start the animation? What? What? Yeah, I don't see one either. So let's go over the sample answer and see what they wanted us to take away from this. Most of the earthquakes hit the west coast of North America and South America. So that makes sense because remember when we looked at our pictures, we had all of those pictures in all of these earthquakes here in South America, like right here on the west coast and on the east coast. So just write something about that for the sample answer. So in other words, Texas is not on the west coast, Nick. So that means they're not going to get that many earthquakes. So, yeah, so write something like that because it looks like what's happening is all of the plates if we zoom out, all of the plates are like right here and right here. That's why you'll see earthquakes here in Australia, here in China, here in like Africa, it's close to some. And there's no fault lines like in Texas. So I better not see Texas in your answer unless it's like there's not that many earthquakes in Texas. Oh my gosh. And then kind of rate your answer here. I don't know what they're trying to say here. There's no math in this activity, guys, so I'm not going to be worried about this one. It's just more observation, so make sure you're right your answers correctly. Nick, I expect to see like a whole essay on why Texas doesn't work. All right, guys. So this next one, we're going to be comparing earthquake compared to the initial earthquake. So here it's telling us we're going to compare to this earthquake right here. So we're comparing the earthquake in Peru compared to an earthquake off the coast of California. So this one was 6.4. This other one was 4.5. So when we enter this in the calculator, we're going to go log of 6.4 divided by 4.5. So if we do this, where's my Google calculator? There it is. So I'm going to clear this out. I'm going to type in log of, I forgot my numbers, 6.4 divided by 4.5. It's about 0.15 times greater. That doesn't seem right. What did I do here? That cannot be right. How many times approximately greater is the magnitude there? Why isn't that working? It should work. Was I supposed to subtract these? Finally, approximately how many times greater is it? The only thing I can think of is I was supposed to kind of use the log rule where I can subtract the difference. So I can do log of 6.4 minus log of 4.5. Nope. Well, we know that log rule works at least because we got the same answer. But I'm confused as to why it's not telling me how many times greater is. Log of, yeah. Oh, derp. I'm sorry, guys. I realized how I derped. IO was supposed to be the initial amount, so this is supposed to be the 1. And then we're trying to see how many times greater it is, so we're supposed to do this. So in other words, like I said, don't worry about that 1. So we're just going to do log of 6.5. 6.5, close that up, divided by log. I keep trying to type in the word log. I keep forgetting it's not Desmos. Log 4.5. Hit that. 1.2 times greater. Okay, now I'm confused. So let's see what they want. Incorrect. It's going to be 10 times greater, and every increase is by 10. So again, we know it's at least 20 times greater. Or sorry, 100 times greater. Because going from 0.5, 0.4 to this, that's 10 times greater. So going from here to here, that's going to be 0.9 out of 10 times greater. So it's going to be about 19 times greater. But I don't know how they want us to plug that into a calculator. 79 times greater? Okay. I am not okay because I don't understand how they did this. So they want us to find, okay, so they want us to find the difference. That's going to get us a 1.9. And then we're doing, okay, because this is the power of that. All right. Then we get that 79. But if I wanted to figure this out as a log, hold on. So let me kind of work this out. I'm sorry, guys. Especially the people watching this, they're like, this guy doesn't know what he's doing. And I don't. But that's the point of this class, is so we can learn together. So what we're doing here is we're doing this log 1.9 is equal to this 79. So this is our answer, which we still don't know, by the way. So in other words, if I wanted to figure this out, so the only way to figure this out as of right now is literally to subtract and then plug it in. So that's when we're going to get into how to solve for it using logs, log base 10. So the next question is, so if I took log of 79, I would end up getting this 10 point whatever. All right. Does anyone want me to go over that? I know that was very confusing, but you guys kind of follow through with me as I was learning it? Okay. So remember, we're subtracting these. That's going to give us our exponent. So think of these as the exponent here. And that'll give us our answer. So we have to do this minus this will give us our answer. All right, so intensity of sound. So here's another one, but this intensity of sound, we're going to have an initial value of 10 instead of 1. So there's always going to be a 10 right here, and there's going to be this little factor. This IO is the smallest sound we can hear. So if I go back to Richter scale, remember that Richter scale, the smallest one we can read for IO is 1. The IO for Richter scale is 1. The IO for decibels is 10 to the negative 12. And it doesn't look like we'll have time. Just to make sure we have time to go over it entirely, we'll do this for the next class, all right? Did you guys understand the Richter scale one, or do you want me to go over it again? Because I know that one I wasn't that convincing on. Okay, so we're trying to find how much greater this is, right? So this is the Richter scale model of the two things we're looking at. So if we're going over 1 times greater on the Richter scale, it's always like 10 times greater, right? How intense it is. But in this case, we're going over like an unknown amount. So it's 6.4. We want to figure out how far apart these two are. So we're going to subtract them. So what happens here is we subtract these, we get 1.9. So from here, since the Richter scale, every number represents a factor of 10, we're going to do 10 to this difference right here. So this is the difference. So if I plug this in here, when I plug them into my calculator, I'll be like 10 to the power of, and if I want to get really fancy, I can do to the power of 6.4 minus, what was it, 4.5? 6.4 minus 4.5. Minus 4.5. That can't be right. Oh, it's 6.4. Blah. Why didn't anybody tell me I did a typo? You guys are all watching. Like, you're not gonna. I believe it. So we get that 79. So we can let the calculator do everything, but again, if you guys aren't sure, you can make the difference yourself. And you can do this 10 to the power of 1.9, and you'll still get the same answer. Does that make a little more sense on how to figure out the difference in Richter scale? Cool. So that's what we're doing here. We're doing basically more exponents is what we're doing for Richter scale. Da, da, da. And then we'll get into sound on Wednesday. All right. All right, guys. Make sure you guys are caught up with logarithmic functions. If you need help, again, you can always make an appointment with me so we can kind of go over it to help you understand the mastery test. All right. All right, guys. Talk to you guys later.